Good evening, everyone. My name is Frank, and today I'm going to be giving an overview and demonstration of my final project for Advanced Analog Electronic Circuit Design. So the project that I've chosen this semester is a laser communication circuit. And the way I'm doing that is that my message signal will be coming from an analog discovery 2 going to several major subsystems. So to begin with, we will have the modulator and transmission circuit. In order to do that, I have an this top IC here. This top IC is an AD654. It is a voltage to frequency converter, for which we go to a OP27G op amp. That op amp, it scales the voltage and offsets it to this laser diode, so our operation mode will be between 3.3 and 5 volts. That diode will change its intensity over this photoresistor, which will go to a max 913 comparator, which will remove any amplitude modulation. Then it will go to an IC multivibrator, monostable multivibrator, which will generate pulses of a fixed width, and then to an integrator circuit, which will restore the original waveform. So the first component in the modulator circuit is the AD654 voltage to frequency converter. So what it does is that it uses an RC network to program the frequency of an output set of pulses. So for this demonstration, I'm going to be giving the input just a 1 volt DC signal, which should output a 1 kilohertz square wave. And the voltage amplitude of this IC should be 12 volts, as a pull-up resistor is connecting it to the 12 volt logic level. As you can see here, I'm giving the input to the AD654 a 1 volt DC signal, and the output of that AD654 is a approximately 1 kilohertz sine wave from close to 0 volts to 10.7 volts as it's being pulled up to close to the 12 volt logic level. So from the output of the AD654, it goes to the transmitter circuit, which is the op amp that I had mentioned earlier. So right now, the op amp is designed to modulate the output waveform between 3.3 volts and 5 volts. I do that by attenuating the output of the AD654 and then providing a voltage offset to keep the voltage at an average of approximately 3.9 volts. It's designed for 4.2. So in this waveform here, in this oscilloscope output here, channel 1 is the AD654, and it is going between 300 millivolts and 10.7 volts at 1.1 kilohertz. And channel 2 is the blue waveform, which is the output of the op amp in the transmitter, and it goes between 3.5 volts and 4.3 volts, which is within the operational range of the diode. For testing purposes, the diode was disconnected at this moment. But from there it goes to a photodiode on the receiver circuit. Now, once the modulated waveform gets to the receiver circuit, it goes to a max 913 comparator, which will remove any amplitude modulation from the signal. So in order to simulate that here, I have a 1 kilohertz 1 volt pulse going into the input of the max 913. And as you can see here in the output, we are going between 3.8 volts, and in this case our logic level is 5 volts and not 12, between 3.8 and 1.5 volts. So for some reason here it is not quite working as intended. It should be going much closer to 0 volts and not 1.5, but it is at the correct frequency of 1 kilohertz. Next, from here it goes to a multivibrator, which generates pulses of a fixed width, which will feed into the integrator. So let me set that up and I will provide a quick demo of it. Okay, so we are now connected to the HC221 multivibrator, which will generate pulses of a fixed width when it detects a zero crossing. So in this demo, the blue is still the max 913 with a 1 kilohertz square wave, or 1 kilohertz pulse going into it, and the yellow is the orange is the output of the pulse generator. So as you can see here, if I increase the frequency of the input square wave from 1 kilohertz to 2 kilohertz, I'll do that. I can see here that the frequency going into the MAX 913 has increased to 2 kilohertz. Change focus. But we are still generating pulses from the HC221 at approximately 500 microseconds per pulse. The pulse width stays the same in each case. So from there, we go to the integrator circuit. Finally, we have the output of the MAX 913 comparator in blue, and then on the top in orange we have the output of the integrator. And as you can tell, that once all of the fixed pulses go through the integrator, it closely resembles the input waveform. There is a bit of oscillation at the start of each square wave, but it does resemble the input, the original input. Finally, this is what everything looks like when going from end to end, where the input is a sine wave going into the 8654 voltage to frequency converter, and the output is the output that is being measured from the integrator circuit. Unfortunately, not everything is going to plan. I unfortunately don't understand why this is happening the way it is, but I think what is going on is that, also just to show this, no matter how I point the diode, how I point the laser at the diode, it does not seem to make a difference in the circuit. What I believe is happening is that whenever the incoming or outgoing from the transmitter into the receiver waveform is hitting the voltage divider, it is not getting close enough to 0 to reset the comparator. So that output is staying high the entire time, and it is not changing enough, or the integrator is going to a DC voltage because the comparator is never going close enough to 0 to trigger the output low. But that is all I have, and thanks for watching. This is the end result. So once again, we have this breadboard on the left is the modulator and transmitter. We have the 8654 voltage to frequency converter, the OP27G op amp underneath this, underneath these probes here. Here I have our laser diode. It's a 635 nanometer red. And then we go to our receiver, which is the voltage across a photoresistor to a MAX 913 comparator, which removes any amplitude modulation, an HC221 multivibrator, which will generate pulses of a fixed width, and finally the integrator, which was another OP27G. In theory, this should be able to recreate the original message signal waveform, but unfortunately, due to imperfections in the circuit, not everything went according to plan, but at the individual level, the individual subsystems work, but unfortunately as an entire system, it did not quite work as intended. Thank you.